Welcome to The Explainer. Today, we're diving into a technology that is, and I'm not exaggerating here, completely revolutionizing computing from the inside out. It's called eBPF, and it's basically giving developers superpowers inside the Linux kernel. We're going to see exactly how. Okay, so let's start with the fundamental problem. The Linux kernel, the absolute heart of our operating systems, it's built to be a fortress. It's powerful, it's stable. But what happens when you need it to do something new? How do you give this fortress new powers without, knocking down the walls? It's always been a huge dilemma. For the longest time, you really only had two bad options. Option one, you could try to modify the kernel's source code directly. This is an incredibly slow, political, and frankly, painful process. We're talking years if you're lucky. Option two, you load something called a kernel module. Now this is fast, but it is so dangerous. It's like performing open-heart surgery with a chainsaw. One tiny little bug, one mistake, and the entire system comes crashing down. But what if there was a third way? What if you could actually have the best of both worlds? What if you could program the kernel on the fly, at runtime, without ever having to touch the source code, and, this is the crucial part, without ever risking a system crash? Well, that's exactly what we're going to get into. This is where eBPF comes into the picture. And honestly, the best way to get your head around it is with this analogy. eBPF is to the Linux kernel what JavaScript is to a static HTML page, right? HTML gives you the basic static structure of a web page, but it's JavaScript that brings it to life, that makes it dynamic and interactive. In the same way, the kernel provides the structure, but eBPF lets you run these little event-driven programs inside the kernel, safely in a sandbox, transforming the OS from this static thing into a fully programmable platform. Now, what's really cool is that eBPF didn't just pop up out of nowhere. It's been evolving for decades. It actually started way back in 1992 as a simple little tool for filtering network packets. But the real game changer, the moment everything changed, was in 2014, when it got this massive upgrade and became a general-purpose virtual machine living inside the kernel. And since then, with things like XTP for insane networking speeds and backing from all the tech giants, we're talking Meta, Google, Microsoft, it's become a truly foundational technology. So how does all this actually work without blowing up the system? Well, it follows this really careful step-by-step lifecycle. A developer writes their logic in a restricted version of C, compiles it into this special eBPF bytecode, and then loads it into the kernel. But, and this is the important part, before that code is allowed to run, it has to get past two critical gatekeepers. These gatekeepers are what give eBPF its superpowers of safety and speed. The first gatekeeper is the absolute secret sauce. It's the cornerstone of eBPF's safety. It's called the verifier. You can think of it as the toughest, most merciless security guard you've ever met. Before your code runs, the verifier analyzes every single possible path your code could take. It mathematically proves that your program can't crash the kernel, can't get stuck in an infinite loop, and can't touch memory it's not supposed to. If it finds even the tiniest hint of danger, your code is rejected. Flat out, no exceptions. So once the code has been proven to be safe, it gets handed off to the second gatekeeper, the just-in-time or JIT compiler. This is all about raw performance. The JIT takes that generic, portable bytecode and, right before it needs to run, translates it into the lightning-fast machine code that's native to the actual CPU it's running on. This completely gets rid of any performance overhead from interpretation, and it allows eBPF programs to run at pretty much the same speed as the kernel itself. It's incredible. And look, this isn't just hype. The impact has been so huge that even Linus Torvalds, the creator of Linux, has praised its power. He totally gets it. He highlights how it lets people add these specialized, on-demand functions to the kernel, which is exactly the problem it was designed to solve in the first place. Okay, so let's talk about its three main superpowers, starting with high-performance networking. This is really where eBPF first made a name for itself. You've got companies like Meta and Cloudflare using it to build these unbelievably fast load balancers and DDoS protection systems that can just chew through massive amounts of traffic. And in the whole Kubernetes world, it's the engine behind tools like Cilium, and it's completely changing the game for how we do container networking. Second superpower, deep observability. This one is huge. Because eBPF lives inside the kernel, it can see everything. I'm talking every system call, every network packet, every single file that gets opened. This lets us trace and profile our entire system with almost no performance hit. It even enables this wild idea of zero instrumentation monitoring, where you can get incredibly deep insights into what your application is doing, like, say, tracking every single database query or counting failed logins, without ever touching a single line of your application's code. And that brings us to superpower number 3, security. eBPF gives you the perfect vantage point for watching over your system. It can see malicious behavior as it's happening, like someone trying to access a file they shouldn't or making a suspicious network connection, and it can block it in real time. Projects like Falco literally use eBPF as their eyes and ears inside the kernel to spot and stop threats before they can do any real damage. But of course, like with any really powerful technology, it's not some magic bullet that solves every problem. The reality is a lot more complex, and the journey to get here hasn't been without its share of challenges and debates. For example, if you go back and look at some of the early discussions online, you'll find critiques just like this one from a user on Reddit. They pointed out that eBPF programs were limited to these short snippets of code, and more importantly, that they couldn't even contain loops. And you know what? At the time, that was a totally valid concern about the text limitations. But this is the great part. The technology evolved. As other users in that same discussion pointed out, newer kernel versions came along and added support for loops, as long as the verifier could prove that they would eventually end. And even before that feature existed, developers had clever workarounds. This little exchange really just perfectly captures how quickly eBPF has been maturing. And that whole story brilliantly illustrates the real challenges that people face today. First off, writing eBPF is complex. It's got a steep learning curve. This is not Python. We're talking low-level C programming. Second, what you can do is tie the specific kernel versions, which can be a huge headache for deployment. And the verifier, while it's our safety net, can sometimes be too strict and reject code that's actually perfectly safe, forcing you into these frustrating workarounds. And finally, if you don't manage them correctly, these powerful programs can become a new security risk themselves. So with all those challenges, how does it really stack up against the alternatives? Well, when you lay it all out, you can really see its unique value. Kernel modules are super fast, but they're incredibly dangerous and a nightmare to maintain. Other tools have their own trade-offs. eBPF really hits this unique sweet spot, giving you the safety of a sandbox, the performance of near-native code, and a much lower maintenance burden. So if there's one thing to take away from all this, it's this. eBPF represents a truly fundamental shift in how we think about operating systems. The OS is no longer just this static gatekeeper with a fixed set of rules. It is becoming a dynamic, programmable platform, one that we can safely extend and innovate on while it's running. And that really just leaves us with a final thought to chew on. Honestly, we have only just begun to scratch the surface of what's possible when the kernel itself becomes programmable. So as we continue to push this idea outwards, making our systems more programmable from the very core, the real question is, what incredible new innovations will this unlock next?